Okay, so today we're going to do a review of vectors, and then we're going to talk about electric fields. So the earlier lectures, the earlier discussions were about electric forces. So we didn't actually talk about electric fields. So today we're actually going to introduce that topic. So uh, what you're about to see is a little bit of a review from Physics 1250. So if you had Physics 1250 from Marion, you might have seen these slides, some of these slides before. So I just wanted to say that in case you recognize it. But what I want to do is I want to give you sort of the bare minimum of what you need to know about vectors for what follows. There's going to be a fair amount of vectors in Physics 1251, a little bit in 1250, but a lot more of it in Physics 1251. So it's important to sort of review that. Vectors are kind of an abstract idea, but there's many different things that are vectors. Wind speed is a good example. So when I like this image because it sort of encapsulates both the direction of the wind and the speed of it. And so you can kind of see that on the day that this snapshot was taken, there's some pretty good wind going on here in North Texas. And the longer these wisps, the faster the wind is going. But it also tells you what direction that it is, because wind has both a direction and a speed. So wind is a classic vector quantity. I can click this link, but unfortunately today is not a super windy day in the U.S. So there's a little bit of wind here and there, a little bit of stuff over Florida. But so you can kind of see the wisps kind of moving, which is kind of nice. But maybe I should have chose a windier day to kind of show this off. But another way of showing the same information, and this image was made on the same day as the plot from the next page. So this is showing, again, the same information, where the length of the arrow shows you what the speed of the wind is. The direction of the arrow also tells you the direction of the wind. And then just for fun, they sort of color-coded it. So the faster the speed, the more towards yellow and orange and red that it is. But again, it's encapsulating the information of both the direction and the speed of the wind, because wind is a classic vector quantity. What do you need to know about vectors? One of the things you need to know is that they're all secretly triangles. Whether it's explicitly stated or not, they are all triangles, basically. And they're all a special kind of triangle, which is that they are right triangles. And because they are right triangles, that means that everything you know about right triangles is still true. So Pythagorean theorem, so a squared plus b squared equals c squared, still totally valid in the context of vectors. It's going to come up quite a bit. All the trigonometry stuff that you know still comes up. Don't forget SOHCAHTOA, right? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent, things like that. Everything you know about right triangles is still true here. The sides of the triangle are referred to as components. And the longest side is what's called the magnitude. And so because we know Pythagorean's theorem, we square the two components, add them together, take the square root. That gives us the magnitude of this vector. So these things are connected. Now, at this point, you might be wondering, oh, all right, so it's a lot of math. It's a lot of sort of like highfalutin stuff, elegant, but how useful is it? Well, here's a situation where the components are useful. I'm going to give you a couple different situations where the components have a real physical meaning. So if you're hiking and you go 100 paces this way and 120 paces this way, you will end up at the same location if you just sort of, assume a particular angle and go a particular distance in that direction. So the components of this vector, going from here to here, the components of this have a real meaning if you're hiking, right? I'll give you an example on the next page that has components of the wind. So again, the distance there's a real connection between the distance here and the components as well. All right, so let's here. What I mean by the wind, the components of the wind, the x and y components of the sort of wind vector has a real meaning. Well, let's say you have some device that can measure the speed of wind, right? So the wind blows and it turns this little thing, and we can measure how fast it's turning, figure out how fast it is. So if we use this to measure the wind speed, and let's say that this is the wind speed, and you'll notice that 3 squared plus 4 squared does in fact equal 5 squared, by the way. But if we use this little fan and we set it like this to measure the speed, what are we going to find? So if we set the fan sort of like perpendicular to the direction that the wind is blowing, not a trick question. If the wind's blowing 5 meters per second and we're perpendicular to it, it's going to give us 5 meters per second. But if the fan is more like this, more vertical, what is it going to measure then? Well, if it's vertical like that, then the wind is only going to be moving left and right. And so if we do it like that, it's just going to give us 3 meters per second, right? Because it's not the full 5 meters per second. It's sort of at an angle to it. And then if we sort of rotate the fan to be in this other direction, what are we going to find then? Well, not a trick question. We're going to find 4 meters per second. So again, the components of the wind, as abstract as they are, there's a real meaning to them, a tangible meaning to them. So in terms of the notation, vectors, you often see vectors with this little arrow on the top. So I like to say vectors wear hats. And a notation that you'll see is kind of an absolute value looking thing like this. It's not really an absolute value because, if this was -3, we wouldn't take the absolute value here. No. This is shorthand for calculating like the length, calculating the hypotenuse there. Taking the squares, add them together to take the square root. When you do this operation, when you calculate this thing, often you'll see people drop the vector notation because this quantity, this is basically the speed of the wind. It's just a number. It doesn't have a direction, so you don't need a vector anymore, and you often see the arrow on the top disappear. Another way of writing this vector, the notation that you'll see, is like this. So you'll see this is equal to the velocity in the x direction times I hat plus the velocity in the y direction times j hat. So these are referred to as unit vectors. If there was a velocity component in the z direction, it would be k hat. But for today, we're just doing 2 dimensions to keep it simple. You will see this notation again in engineering statics. So if you're in the engineering statics currently, we're going to take it later. We're trying to figure out like how much stress and strain can a bridge hold, those sorts of things. You'll see the IJK notation appear then. And so this is not just a physics thing. You're definitely going to see this over again. So that's the review of vectors. Now we're going to sort of start to get back to electricity and electrostatic forces. All right. So last time we talked about electric forces. We talked about how the Coulomb force goes as 1 over r squared, right? So if you increase the separation by a factor of 2, the force goes down by a factor of 4, things like that. And we talked about how the electric force is just another force. Gravity is a force, string tension is a force, friction is a force, etc. And so electric forces are just another force, and there's a whole class of problems where you can treat it like that, and the last worksheet was a perfectly good example. We are going to introduce a new idea called electric fields. And the idea of the electric fields is that it is always going to point in the direction of the electric force on a positive charge. Now, why would you want to come up with this idea? I'll explain that in just a second. But if you have 2 charged objects, the electric field on this one, if they're both positively charged, the force on this one is going to be this way, so the electric field would be off that way because it's repelling. And so instead of thinking of things in terms of the total, all the total forces, the net force, what we're going to do is we're going to take that force and divide by charge q. So if we have two charges, instead of thinking like, well, what if I had at this location, what if I had 1 nanocoulomb of charge? What would the force be? And you run the numbers, you come up with that. And you say, all right, what if I had 5 millicoulombs? And you run the numbers and you figure out what that would be. But after a certain point, this gets to be pretty tedious. And instead of having some quantity that depends on what kind of a charge do you actually have right here, you'd rather, at this point in space, you'd rather sort of know, sort of what this number is, so that if you had the charge, you could very quickly figure out what that force is. So another way of saying that is that if you had a bunch of charges, you have a charge here and a charge here and a charge here and a charge here, and you wanted to map them all out, and you wanted to make a map of what direction that the electric force would be. Well, you'd have to make 2 maps. You'd have to make a map for the positive charges, because the positive charges would go in a particular direction. They're repelled away from positive charges. They're attracted to negative charges. And then you'd have to make a whole nother map for the for the negative charges, because the negative charges are attracted to positive charges and repelled from the negative charges. So instead of making 2 maps, we can make 1 map, and we'll call that map the electric field. So there's a convenience in terms of, from a cartography standpoint, there's a convenience in terms of having to do this calculation over and over again. So it saves you time there. The third reason that we're going to lean towards talking about electric forces as we're going to tend to talk about electric fields as opposed to electric forces, is that if you get deep into physics, which I encourage you to do, you'll discover that we think that fields are the fundamental thing, and that the forces arise because of the fields rather than the fields arise because of the forces, if that makes sense. So I'm not going to dig deeper into this, but this is certainly one of the reasons why we talk about it in the way that we do. Electric forces were vectors, as I talked about last lecture. If we're just going to divide by a test charge, divide by q, that means the electric fields are a vector, right? So it has a particular direction that it's pointing, and it also has a magnitude. So for example, here's an example of electric field. So electric fields, we got a little axes here, so plus x, plus y there. What would this be in vector notation? Well, by vector notation, I mean the I hat, j hat thing. Well, overall, we're going positive x, and we're going a little bit positive y. So I would say that this looks to me like 2 this way and then 1 this way. So this is another sort of fancy way of writing the I hat and the j hat. Just depends on the font that you're using. What would this be? We still have the x and the y axes. What would this look like? Well, we've got overall going this way, right? So plus x, but it's sort of down in the y direction. It's going to be a negative. So that's just an example of how to write these things. All right, so that's how you would write, this sort of a thing. How do you write this? This seems much more complicated than what we just did. So how do we actually write down an equation for, the electric field around this positive charge here? Or, I could draw it like this. Well, let's talk a little bit about gravity first. So let's just sort of take a break from all this crazy electric stuff and just think about gravity. So gravity sucks, right? So gravity is always pulling towards the Earth. And so if I was going to write this in vector notation, I would say there's a force of gravity. This is the magnitude of that force that we talked a little bit about in Physics 1250. If I was going to write this as a vector, I would write it like this. So I would say, so you notice how there's an arrow here now on the force of gravity. Have all this same stuff. we have this crazy thing, which we'll talk about in the next slide, calling that r hat. We still have the distance squared. We also have a minus sign, which we'll talk about in the next slide. So, all right, let's break this down. So this r hat is also called the radial unit vector, and the equation for it is I'll give you the equation for it in just a second. The thing to note about the radial vector is that it's always pointing away from things. Always points away from things. So it's pointing away from the Earth in all directions. Except if you put a minus sign in front of it, then it's always pointing towards the Earth. And that's exactly what we want for our gravity vector, right? Gravity sucks. It pulls things towards the Earth. So that's part of the trick, is that this always points away, and then we put a minus sign out there and make sure it points towards. Now, what is the equation for this? So it depends on the angle. Depends on the angle that you are from the x-axis. But this is the equation for the r hat vector, the radial unit vector. And what's interesting is to take the magnitude of this vector, which you're going to do in a second. Before we do that, I just want to double check that the values make sense. So for example, if theta equals 0, right, theta equals 0, so cosine of 0, sorry, let me go back here. If theta equals 0, cosine of 0 is 1, and then sine of 0 is 0. So if theta equals 0, that means r hat equals I hat. Okay, so does that make sense? All right, if theta equals 0, r hat is in the x direction and not at all in the y direction. Yep, that works pretty well. If theta is equal to 90 degrees, then sine of 90 is 1, so you get a 1 over here. But cosine of 90, so that cosine curve is dropping and it hits 0 at 90, is 0. So if theta is equal to 90, then r hat is equal to j hat. Does that make sense? Yep, that's exactly right. That's still pointing away from the Earth. So this equation works out. And what we can do is we can actually take the magnitude of this vector, right? So we can take the components and square them and add them together. And maybe you recognize this, maybe you don't, but whenever you add cosine squared to sine squared, you end up with 1. So for example, if you go to your calculator and you put in any number, cosine squared blah plus sine squared blah, where blah is the same thing, you'll find that it adds up to 1. Exactly why that happens, it's not too hard to track that down. But anyway, this adds up to 1, and so the square root of 1 is 1, right? And so we can say that the magnitude of this radial unit vector is 1, which is why we call it a unit vector. And that's really important because we don't want to change the magnitude of this gravity vector, right? The magnitude's correct. We already know that it has to be this force. We just want to put in the direction of it, and so the radial unit vector kind of helps to do that. So that's how you do this with gravity. How do you do this with electric fields? Well, you do something similar. So you do something like this. So you say, all right, the electric field from one charge, a charge, depends on what that charge is. It depends on your distance squared to that charge. It depends on the Coulomb constant we talked about last time. And then there's this r hat vector that is always pointing away from the thing. So this is the electric field vector. And if this is positive, right, so r is positive, k is positive. So if q is positive, then the electric field is always going to point away from that charge. So if any positive charge, electric field is going to point away. But if it's a negative charge, it's actually going to do the opposite. The electric field will point inwards. Anyway, so this equation kind of codifies, this sort of a thing and this sort of a thing, right? Because we know that electric fields always point in the direction of the force on a positive charge. And so if I put a positive charge over here next to this other positive charge, well, it's going to repel. It's going to want to go this way, right? And sure enough, that's the direction of the electric field there. If I put a positive charge up here, it's going to want to repel, and so it's going to send it up this way. And sure enough, the electric field is up in that direction. So for full disclosure, this is a nice cartoon picture, right? But in reality, there's a 3D thing. We live in a 3D world. And so there's a nice kind of utility to kind of see what these things look like in 3 dimensions. So you can feel free to play around with that. I might go over that in a Zoom meeting at some point. So there's some nice apps that you can download that actually help to build. So I'm quite proud of these. So again, going back to electric fields point away from the electric fields point in the direction of the electric force for a positive charge. The fields kind of have to follow the arrows, where you sort of draw lines between these things. So this is sort of the electric field of vectors, you could say, or at least the direction of it. You notice that they haven't actually, the length of these arrows don't change, but that's just because of the way they plotted it. This is what electric field lines look like. So they point in the same direction as the electric field vectors, but you sort of draw lines through the little arrows. And the reason to do this is that it's understood that if these lines are closer together, the strength of the electric field is more. And so it's a nice way of codifying that idea that the closer you are to one of these charges, the stronger the electric fields are. That's right, it always points away. Now if you have a negative charge, you have the electric fields pointing towards it, not away, right? Because if I put a positive charge up here, positive charge is going to be attracted to this negatively charged thing, so the direction of the force on a positive charge is down, so the direction of an electric field is going to be down. Same thing if I put the positive charge out here, it's going to be attracted. The force is going to be this way, so too is the electric field. So that works. And then it's also the same thing with the field lines, except that instead of the arrows pointing away from the charge, right, the arrows are always pointing towards the charge. It's still true that because these lines are closer together, the electric fields are stronger. It's just that it's in the different direction. Under no circumstance are there negative charges that have arrows going out of them. And there are no positive charges that have arrows going into them. So no matter how complicated things get, that's just not what's going to happen. Let's try to do something. Let's try to do the next most interesting thing to do. Let's put a positive charge next to a negative charge. So here they're sort of isolated, but if we put them together, you end up with something like this. And so this is what the electric fields look like, right? So if you put a positive charge in between two of these things, it's going to repel from this thing, right? It's going to be attracted to that thing. So the force is very clearly this way, towards the negative charge. If I put a positive charge up here, well, it's repelled this way, right? It's going to be repelled from the positive charge this way, but it's going to be attracted to, it's hard to do. It's going to be attracted to the negative charge this way. So we've got a force towards my head, right? And then force down like that. Those two things cancel out, and overall the force is sort of this way, if that makes sense. Sorry, it's hard to do this. It's hard to do this in a green screen. But that's the basic idea, is that that's ultimately why the arrows are sort of parallel out here. So if you were to draw the electric field lines, they would look something like this, and you can probably tell the electric fields over here are stronger than they are out here because the lines are closer together. The arrows are all sort of pointing this way, sort of pointing this way in the middle, but then it's opposite over here. So this is, a three-dimensional impression of what electric dipole looks like. We did try to go to the trouble of making the arrows a little bit longer, because it really is stronger the closer that you are to these charges. So you can check that out if if you want. This is sort of a video of what that looks like. A nice part about the video is that you do see the vectors in the middle, because in the middle the electric fields are going to be particularly strong. Now in reality, you don't actually get this sort of like flower-looking thing for the electric field structure. This is just sort of an artifact of the way that we're drawing it, and an artifact of humans being incapable of seeing, four-dimensional space or something. But hopefully you can get an idea of what this actually looks like in 3D. Again, no matter how complicated things get, you'll never have an electric field coming out of a negative charge, and you'll never have an electric field going into a positive charge. That's not how it works. Okay, so now we're going to think about electric fields not just sort of in a qualitative sense or just sort of a general sense, but we're actually going to try to calculate the electric field halfway in between a positive charge and a negative charge. So we want to know what the electric field is like in the middle of that. To give you an example of a situation where that happens, this is a Wimshurst machine. We actually have this machine at Marion. So if we were in person, I'd be showing it off to you. Basically, this thing spins around, and it's a long story exactly how this works, but one way or another, you get a bunch of positive charge on one side and negative charge on the other side. I can play that back again. Now, when I say positive charge on one side, what I mean is that you have a lack of electrons on one side, leaving behind positive charges, and you have an excess of electrons on the other side. And this happens until the point that the electric forces between these two things, right? There's air in between here. So think of a little air molecule here. There's an electron in that air molecule. So let's say this end is positive and this end is negative. There's an electron in that little air molecule that's attracted to the positive electrode. And then the nucleus in that air molecule which is positively charged, is attracted to the negative electrode. And there's a force on that electron. There's a force on that ion, positively charged ion, until the point where the electron actually gets ripped off of that air molecule. And once it's ripped off, it's free to move. And if it's free to move, then it's going to act like a conductor. So earlier I was saying that plasma is a conductor. Well, that's what you're doing. You're creating a plasma in the air when you make a spark, whether it's tiny or whether it's lightning. And so what that does is that once the electrons are free to move, well, then the electrons are going to move towards the positive end, and they're going to move away from the negative end. And so they're going to keep doing that until there's no longer an excess of electrons here, and there's no longer, positive charge over here, that it all sort of neutralizes out. So one thing to say about this is that, these electrodes, this side is not always positive. When a spark goes across, it goes back to zero. Right? But then very quickly the charge accumulates again. So it's not that this is always ever positive and this is always ever negative. It's always sort of going from zero up to that charge, back to zero, up to that charge, things like that. But in any case, what we want to do is we want to figure out what's the electric field halfway in between these things. And so if we knew this charge and we knew this charge, we'd like to be able to figure out what this electric field is. So this is, so we're going to do that. So let's say that one of these things is 10 nanocoulombs and the other one is negative 10 nanocoulombs. We have our electric fields here. And we're going to, at the point in the middle of these two things are going to add together. It's true for anywhere on this page, but it's also true of the middle. So let's say there's some distance d between the two charges, and we really want to know what is the point. We really need to know what the E field is in here, is our goal. So we're going to do that by just adding the electric fields together. So the electric field in the middle is the electric field from this thing plus the electric field from that thing. So let's break this down. So this is our charge number 1. This is our charge number 2. So this turns into that. Okay, and the reason it turns into that is that the origin of our coordinate system, x equals 0, is right on top of our charge, right? So we're further away from our charge. That distance is x squared, right? We're not going to worry about y squared today. So that's why there's an x squared in the bottom. And then this radial vector, radial unit vector, is always pointing away from this charge, right? And so over here, the radial unit vector would be this way. Over here, the radial vector would be this way. But over here, the radial vector is this way, right? And so our radial vector is in the positive x direction. That's why there's a plus I hat there, okay? Now we can think about this one, right? So this one, if you think about the distance here along the x-axis, you know, you're right on top of it if x is equal to d, right? So technically there should be like an x minus d thing going on here for the distance. But interestingly, there's a minus I hat here, right? So why don't we just use plus I hat again? Well, remember that the radial vector is always pointing away from the charge, right? So even if it's a negative charge, the radial vector doesn't care whether it's a positive or negative charge, right? We're going to sort of take into account that this thing is negative with this q here. But at the stage of just figuring out the radial vector, the radial vector doesn't care whether it's positive or negative. So it's pointing away in every which direction. So over here, the radial vector is this way. Over, you know, up here, the radial vector is up this way. But over here, the radial vector is this way, which is in the negative x direction. So we need a negative I hat here. So what we're going to do in just a second is combine these two things, add them together, like so. Something that makes this a little bit easier is that we're halfway in between these two things. So x is d over 2. So we're going to get a d over 2 squared, and we're going to get a d over 2 minus d squared. D over 2 minus d is just d over 2, right? In other words, the distance is d over 2 to both of the charges, which is fine. And we can square that out. And it's tempting to, you know, one wonders if this is going to all cancel out, right? Because there's a plus I here, there's a minus I here. So you might be a little bit worried that we did this wrong, except that Q2 is negative. So when you put that negative in there, the negative times a negative makes a positive. And at the end of the day, you end up with negative times a negative is a positive. You end up with something like this for the strength of the, you know, for the electric field vector in between these two things. So if we know the distance, we know the charge, we know the electric field is going to be like this. So there you go, and you can run the numbers and see what you get. Now, what's interesting to me is how do you make sparks, right? So we all want to make sparks. That's the fun part, right? So how do you make sparks out of all this? So unfortunately, there's a barely perceptible kind of horizontal line here. And this horizontal line is at 10 to the 6 newtons per coulomb is our field strength. And the way that you get sparks is that if you have, say, a positive charge here and a negative charge here, if the electric field is above 10 to the 6, well, then the air can potentially ionize. If the air can ionize, then you can create a plasma. If you can create a plasma, then you can potentially create a spark. But the thing is that to get a spark, you know, technically the air is ionizing sort of around here and around here. The problem is that it might not be able to ionize all the way from this charge to this charge, right? So in this case, if this dashed line is the total electric field, I mean these purple and green lines are the electric field for just this charge and just that charge. But if you add them together, for example, they add together and get a little bit stronger out here. So if this goes below the threshold for ionizing the air, then you're not going to get a spark, right? So, oh well, no sparks, right? You can only, you know, it's only strong enough to ionize right close to this thing, but it's not strong enough to ionize all the way across. If the charges were, the fields are a little bit weaker than they would be if there's just one charge, because it's a positive and negative. If the charges were close together, though, say, and the total electric field is now, sorry, it's hard to see this horizontal line. If the total electric field is always above this 10 to the 6 threshold, then you can ionize the air all the way from the positive electrode to the negative electrode. And if you do that, well, then you're going to get a spark, because if the electrons are free, all the way from one side to the other, they're going to move whatever direction they want to move, and they're going to move towards the positive charge and away from the negative charges. So then you will get sparks. And so the question of whether you're going to get sparks has to do with, it really has to do with what is the electric field halfway in between these two things. Because if this electric field is above the threshold, then yeah, you're going to get a spark. But if it's below the threshold, then you're only going to be able to ionize over here, and it's not going to create a channel from one side to the other. So you're not going to get sparks that way. So there you go. I think I already said these things. Now, this is just a conceptual question. Let's just think about this. So let's say that there's a big beefy negative charge, and there's sort of a smallish positive charge. Where, if anywhere along this line, can the electric field be zero? So let you think about that for a second. It has to be along this line. It's not going to be like up here or down here. So somewhere along this line, region 1, 2, or 3, where could the electric field possibly be zero? So let's see. So region 3, where can the electric field be zero on here? So the first sort of, I would say, crucial insight into this question is that the electric field always points in the same direction that the electric force would on a positive charge. So if we're trying to find the place where the electric field is zero, that's equivalent to saying we're trying to find the place where the electric force is zero. So if I took a positive charge, for example, and I put it along here, is there anywhere in region 3 that I will find zero electric force? Well, if I put the positive charge here next to this big negative charge, it's going to be attracted that way. So that force is going to be non-zero. I could bring it back out, and the force is going to be less. It's still overall going to be attracted. So either there is nowhere in region 3 where the electric force can be zero, or it'd have to be infinity, in which case that's kind of ridiculous. But so really there's no place in region 3 where the electric force would be zero. Okay, let's take our positive charge and put it in region 2. Is there anywhere in region 2 that could possibly be zero electric force? By the way, part of the reason why region 3 can't have zero electric field is because we're so close to this big beefy negative charge. The fact that there's a positive charge over here just doesn't really matter, right? Because it's not that big. So if I put the positive charge somewhere in here in region 2, is there any way that could be, the electric force could be zero in there somehow? Well, if I put a positive charge here, it's going to be repelled by this thing, okay? So the force is going to be this way towards me from the positive charge. And then positive charges are attracted to negative charges, so the force from this thing is also going to be this way. So it's going to be a very large force this way, and there's nowhere along this line where that force is going to be small or zero, right? If you're close to here, it's going to be large because you're close to the positive thing. Close to here, it's going to be large because you're close to the negative thing. So nowhere in region 2 can you really find a place where the electric field or the electric force, whichever way you want to think about it, would be zero. But if you're in region 1, it's conceivable that if you're a positive charge here, you might be able to find the spot where you're repelled away from this positive charge, but you're also attracted to this big beefy negative charge. It's conceivable in region 1 that somewhere along here that those two forces would balance and you'd be able to just sort of stay there, not experiencing any force. So the answer is region 1 is the only place where the force can be zero. See, I didn't even give you the answer. That's why you should watch the lectures. So I don't just put the answers on the slides all the time. All right, now this question, so this conceptual question was sort of a setup for talking about this thing. So to me, this is one of the more confusing questions, and I want to break it down so it's confusing not because it's hard, it's confusing because it's just poorly worded and there is no diagram. So welcome to the beginning of my rant. But again, this question is done by all the students in Columbus, and so we got to do it too, right? So I'll read it for you. Two charges, a positive, small positive charge and a pretty considerable negative charges, are 14 centimeters apart. There's a third charge that is placed on the line between the two charges, how far from Q1 should the third charge be placed so that the net electric force on the third charge is minimized? Okay, so when I first read this question, the first thing in my mind, I went back to here and I said, oh, there's a place over here where the electric force should be 0 because those two things balance out. Clearly, that would be a minimized force, right? It's minimized if it's 0. You can't have less than 0. So clearly, this question is asking me to calculate what is the distance from here to this positive charge, right? But it turns out that's not what it's asking. I had to learn that the hard way. So if you plot this out, right, again, this dashed line is the total electric field. If you plot this out, you've got, the smaller positive charge, the big beefy negative charge. At some point, those two things, you see how the electric field from just this one is equal to the electric field from just that one, and then the total electric field drops to 0 here? That's exactly what we've been talking about. What's tricky to realize is that they're not actually asking you to figure out where this is. What they really want you to do is they want you to figure out what this is, the total E field that is minimized. So what's the smallest E field? It's not necessarily halfway in between the two. If the charges were equal, it would be halfway between the two, but the charges are not equal. And so what they really want you to do is find the smallest value of electric field here, which is a decent question, right? Because if the smallest value is above the threshold for ionizing the air, then you're going to get a spark. But if it's not, well, then you're not going to get a spark. So it's a reasonable question to want to know. And so how in the world do you do this? With this, you could sort of try to set the forces equal to each other and try to figure out where that would be. But how do you figure out the smallest value of the electric field? Well, here's my advice on how to do that. So what you want to do is basically you want to follow the same kind of directions we did for the the plus 10 nanocoulombs, minus 10 nanocoulombs. But instead of setting x equals to d over 2, you just want to have this thing divided by x squared plus this thing, the quantity x minus d squared, and then just plot it out. And so once you've plotted it out, you basically have two options. One is you can sort of take the derivative of this thing and set it to 0. Maybe an easier way to do it would be if you have a graphing calculator or using Desmos or something, would be to plot it out, just take the minimum of this function from, the Desmos minimum function. I'm totally happy with that. That works fine for WebAssign. If it's good enough for WebAssign, it's good enough for me. And by the way, you are allowed to use Desmos on the exams, but it has to be in the test mode, and you have to let us turn it off. So anyway, so that's my advice for doing that problem is try to actually come up with a function for what this electric field is as a function of x, and then literally plot that function and find the minimum, is my advice. There's also some problems on homework too that are similar to that. All right. So, okay. So I'm going to take a break there, and I'll continue recording this video soon.